Fantastic. All right, so next up we have Mathilde Fajardy, and that's a terrible pronunciation, but it's acceptable, she says, on designing optimal BECCS supply chains, a water, energy, carbon, land nexus problem. Thank you.
All right, thanks for staying that long. So I'm a PhD researcher at Imperial College London. I'm going to give you some insights from my modeling work on BECCS, especially in the context of the water, energy, carbon, and land nexus. Okay, so you've seen this during the conference. Negative emissions are needed. They are needed sooner rather than later. We're talking about as early as 2030, so time really matters in this analysis. And they're needed at scale. And because they're needed at scale, we have a portfolio of technologies, and we're trying to navigate within this, what we call the negative emission technology trilemma, to find the technologies that can meet a certain carbon removal and energy production, in the case of BECCS, so technical performance, while having limited impact on resources, such as water, land, biomass use, or what we call carbon efficiency, so how much CO2 which is captured in the biomass actually ends up being net removed from the atmosphere, and other broader economic environmental impacts, such as land use change, soil erosion if you use too much agricultural residues, for example, or biochemical flows from nitrogen use, biodiversity impact, etc. So you know the principle of BECCS. We're trying to go from 1 molecule of CO2 absorbed from the atmosphere through biomass to 1 molecule of CO2 stored geologically. And you know that there are a series of steps going from farming to processing, transport, conversion, and CCS. And they all have their own challenges. In this analysis, we focus on energy use. So there will be a lot of different energy use in the form of fertilizers, fuel, chemicals, and of course associated CO2 emissions. And you will have also emissions in the form of land use change, or indirect or direct land use change at the farm level, or N2 emissions from fertilizer application, etc. And then of course you're combining the two more, among the two more consumptive, water consumptive fields, agriculture and power generation when you're doing BECCS. So of course water is a big issue both at the power plant level, so cooling duty of the power plant, and at the field level. And so a last aspect of my analysis is time. If you look at the evolution of cumulative net CO2 emission over the lifetime of a BECCS project, if you take it from a hectare perspective, so you have a hectare of land, you convert it from whatever activity was on that land to biomass production. And so you have a potential direct and indirect land use change here. And then you also prepare your land with fertilizers and so on and so forth. And so you haven't harvested any biomass yet, you haven't captured any CO2, but you have potentially emitted a lot of CO2. So that's your initial carbon debt that you're going to try to pay back over the lifetime of your BECCS project, hopefully as you start producing biomass and capturing the CO2. And so, of course, you want to be carbon negative statically, but you want to be carbon negative dynamically, and you want to see what you actually become carbon negative. So what's your carbon break-even time, and what's the total amount of CO2 captured over the lifetime of a BECCS project? And it's kind of the same for energy. You have energy use at the field level that you need to pay back by producing electricity. So in order to investigate all of these questions, we built another model. We call it the MONET model, which stands for Modeling Optimization of Negative Emissions Technologies. And basically what we're trying to do is to calculate the water use, land use, amount of CO2 removed, net energy produced, carbon break-even time and energy break-even time of a system, let's say the UK, but it could be any other region, that has a BECCS facility, so quite large scale, 500 megawatt, and using biomass, so different types of biomass. We use dedicated energy crops or agricultural residues, grown on different type of land, and basically imported from different regions of the world. And we calculate those metrics from all of the potential combinations. And then we, based on the supply chain model, we can answer different questions, under which conditions, but also when, is BECCS carbon negative? So what are the right combinations leading to BECCS being actually carbon negative? Is BECCS sustainable and resource efficient? So what about the water and the land use? And then in terms of energy, does BECCS deployment actually contribute to the energy system? So is BECCS energy positive? And so based on the supply chain model, we then built an optimization model that looks at what would be the optimal supply chain or BECCS value chain, so a combination of those biomass types and those regions in order for a country to meet its regional carbon removal targets. So if the UK, for example, needs to meet a 50 megaton CO2 removal per year, where should it get its biomass from? Was it from the UK or from other regions? And how does this optimal supply chain changes as we change our objective function? Is it the water use that we want to minimize? Is it the land use? Do we want to maximize the carbon efficiency of the system? So how efficient are we using our biomass at getting this CO2 out? Or is it the energy that we want to maximize? Do we want to maximize the amount of energy we're producing? And how does the picture changes? And we're choosing this multi-objective approach in order to not get just one optimal supply chain, but really to evaluate the trade-offs between different BECCS KPIs. So like any other model, you need a lot of data. So we're trying to navigate in all of those data sets, but what this picture shows you is that some parameters are critical. So for example, if I'm the UK and I want to use biomass for my BECCS facility, sure, I can take biomass locally if it's available, and it will have a certain yield. It will have a certain carbon intensity of processing, especially depending on the carbon intensity of the electricity grid. But I could also get my biomass from, let's say, southern states, which is what's actually being done, or Brazil. And yes, you will have emissions from shipping the biomass from across the Atlantic, but maybe the carbon intensity of your grid there is lower than a lower processing emissions. Maybe your yield is higher, which is actually very important. Maybe you have more marginal land there, which means less land use change potentially. And so all of those parameters have an important role, and it's not as easy as local biomass is better than imported biomass. And this data is very variable as well. Of course, there's a high uncertainty, variability, but also there are a lot of different options of supply chains, and all of this results in a wide range of results. And trying to capture this uncertainty is also one challenge of this work. So we have 3 projects in this PhD work. So the first project was really trying to answer, is BECCS carbon negative in a relevant time frame? So that picture shows you one specific case. So that's the UK importing miscanthus from Brazil that has been grown on grassland. So there is a direct and indirect land use change here. There is a wide range of initial carbon debt. And that's the cumulative emissions over the lifetime of a BECCS project, so the dynamic chart I showed earlier theoretically. And you can see that first you don't have just one line, you have a range of lines. And that's, again, because you could use different carbon footprints, well, you could use different electricity, fuels, and chemicals that have different carbon footprint. You could have different moisture content depending on the fuel that you're using, or the biomass that you're using. You could have a yield increase or carbon content variation. But you could also have a different supply chain. You could look at alternative scenario where you use biofuel instead of regular fuel for transport, or you dry your biomass with biomass and not natural gas. And all of these impact your results. And the key metrics to see here, again, is when does your line crosses the 0 line, so your carbon break-even time. So you can see that you can have a break-even time in this case, where there is land use change, between 5 and 35 years. And cumulative emissions over the lifetime of a BECCS project between 200 and 1,800 tons of CO2 per hectare. And the second question that we asked ourselves in this project was about the resources. In this case, I present the results for the water. We first calculated the water footprint and the water implications of growing a certain type of biomass in different climate, in different regions. And so these are just examples, but you can see depending on which biomass you consider and where you grow it, so UK or LA is Louisiana, you have a very different picture. And then we calculated the total water intensity of a BECCS facility. So you have the cooling duty, and we first calculated the water intensity as a function of capture rate, so how much CO2 you're capturing as a function of co-firing, biomass co-firing. And the gray surface here, which is flat, is the cooling duty evolution as a function of this capture rate and co-firing. And usually when you capture more CO2 and you co-fire more biomass, you're less efficient, so you use more water. But in this case, this surface is virtually flat at this scale because on the same chart we plotted the water intensity of a BECCS facility, including the water footprint of the feedstock. And it's just to show you the magnitude of which the biomass water footprint impacts the total water intensity of the system. And of course, little water footprint, smaller impact on the system. And so, yes, it's very important to improve biomass conversion processes and CCS processes, but really I think the bottleneck here is the biomass sustainability. In the second project, we focus on the energy balance on BECCS. And I think our original question is what is the energy return on investment of BECCS? And is actually BECCS contributing to the energy system? So we had the same reasoning as for carbon. We calculated all the energy contribution along the supply chain. We calculated that dynamically over the lifetime of a BECCS project. And we calculated the net electricity balance from year 0 to year 50. So that's, for example, willow from the UK. So willow is a woody biomass, high moisture content, high drying cost, so high energy, embodied energy in the supply chain. So you realize that even though it's local, net electricity balance is right about positive at the end, and you're not producing so much electricity. And then if these results here translate in terms of energy return on investment, EROI, or LROI, electricity return on investment. And so the blue bars here are the EROI of the pellets, and the red bars are the LROI of the electricity. And you can see that in terms of electricity return on investment, you're above 1 for most scenarios here represented, but not very high, like below 4 or 5. And some scenarios are electricity negative, LROI below 1. And so in some cases, you can have systems that are not actually contributing to the energy system. So deploying the system at scale could theoretically represent a threat also to the energy system. And so a third project that we are doing at the moment is this optimization and investigation of the KPIs, of the trade-off between BECCS KPIs. So here, I'm showing if the UK wants to meet a given carbon removal target, so that's for 50 megatons of CO2 per year, where would it need to get its biomass from in order to minimize either the water use here, the land use here, or maximize the carbon efficiency? First, you can see that the resource efficiency, so how much land, water, and biomass is used for each scenario, changes depending on the objective function. For example, the water here increases threefold between the water minimization scenario and the other scenarios, which shows the high trade-off between water and the other resource efficiency indicators. And then second observation is that local biomass is not very often picked in those optimal scenarios. And so parameters such as high yield, high precipitations, low electricity carbon footprint really outweigh the transport distance. And this is confirmed here. So this is to show you that if we just move the location of the biomass conversion and CO2 storage to, for example, US, so what if the US had to meet this 50 megatons of CO2 target? In the water and China in blue, so US in purple and China in blue. Well, basically in the water minimization scenario, the regions that are picked are the same, which really shows you that in the water scenario, the transport distance does play such a role, and there are some key regions with key parameters that will be better and more sustainable in terms of water use. In this second result, I show some trade-off between water use, so the resource efficiency, and here, and land use change, the economic and environmental impacts. So this map shows you what are the regions picked in order to minimize water use when all of the marginal land that I consider as an input of my model is available. And then I start constraining this marginal land. Is it working? Yes. So I start constraining this marginal land, and what I see is that the same regions are actually selected, even though there's not enough marginal land, so the BECCS system is trespassing on other types of land, such as grassland and cropland, even though this will create very high land use change emissions, which are accounted for in the model. But rather than choosing other regions with low water footprint, it will still choose these regions with a much lower water footprint and trespassing on other types of land. So water use and land use change being two critical issues for BECCS. One should be careful when optimizing these systems vis-à-vis only water, for example. This could be detrimental to other sustainability factors. And the last trade-off that I'm analyzing here is between technical performance, so electricity production, and resource efficiency. And I'm showing the parallel fronts obtained with the optimization problem between the water use, here land use, and carbon efficiency as a function of the the total electricity produced here. And you can see that there's a strong trade-off between these indicators. So here, this point, for example, is the point obtained for when the water is minimized, and this point is the one obtained when the energy is maximized. And you can see that the water increased by several order of magnitudes when it's the case. So my big focus on BECCS technical performance or energy production will be detrimental to BECCS sustainability. And so to conclude, so these are very broad general conclusions, and you can find much more details in the publications. But I guess in terms of policy implications of these conclusions, I think we need to acknowledge the regional variability of BECCS performance. So CO2 removal can be delayed in some cases or non-existent, and that biomass sustainability is the bottleneck. In terms of BECCS contribution to the energy system, we need to define which service BECCS is going to fulfill in the society. Is it carbon removal or is it energy production? Because in some cases, the energy production is not something that will be delivered by BECCS facility. And then in this last analysis, we showed that BECCS supply chains are likely to involve multiple actors from different regions of the world, and how are we going to regulate this multipolar, multi-stakeholder system, and also that the regulation of BECCS will need to be on a multi-criteria perspective, as there are very complex interactions between BECCS sustainability indicators. Thank you.